Look up at the night sky and tell me what you see. A scattering of stars, right, pinpricks of light, arranged in patterns we've named and mapped for centuries. But what if I told you that the universe holds secrets far stranger, far more complex than anything our ancestors could have dreamed? What you're looking at isn't just a sea of individual suns. Many of those lights aren't single stars at all, but intricate families of 2, 3, even more stars, all orbiting one another in a delicate cosmic dance. Now imagine not just 2 or 3, but 14 stars, all bound together by gravity, spinning, interacting, defying everything we thought we knew about how star systems form. Welcome to the bewildering realm of Quattuordecuple star systems. Yes, you heard that right, 14 stars in a single system. It sounds like something out of science fiction, but it's very, very real. And the strangeness doesn't stop there. From bizarre orbital patterns that shouldn't exist to interactions between stars that challenge the laws of physics, these systems are rewriting the textbooks. They raise questions we're only beginning to answer. How do 14 stars form together without tearing each other apart? What kind of worlds, if any, could exist in such a chaotic environment? And what can these extreme systems teach us about the universe itself? In this video, we're going to explore 30 of the most astonishing discoveries scientists have made about Quattuordecuple star systems. Some will fill you with awe. Others might keep you up at night, but all of them will change how you see the cosmos. This isn't just a list of facts, it's a journey to the edges of known physics, a dive into one of the most extreme and rare phenomena in our galaxy. So get comfortable, let's unravel the mysteries of these 14-star marvels, one mind-bending discovery at a time. The journey into this realm of cosmic complexity begins with a single, staggering discovery: the first confirmed Quattuordecuple system. For decades, astronomers theorized that such intricate stellar families could exist, but finding one was another matter entirely. The breakthrough came not from a lone telescope, but from a powerful combination of techniques. By analyzing the subtle wobbles in a star's light, a method known as radial velocity measurement, scientists could detect the gravitational tug of unseen companions. This was paired with the painstaking process of direct imaging, using advanced optics to block the blinding glare of a primary star and reveal the fainter points of light orbiting it. Each new star identified was a triumph, but as the count climbed past 10, then 12, the data began to seem almost unbelievable. The initial reaction in the astronomy community was a mixture of profound skepticism and electrifying excitement. The discovery challenged a fundamental assumption that gravitational interactions in such a densely populated system would make it inherently unstable, destined to either collapse or eject members over a short cosmic timescale. To find one that had not only formed but had also persisted was like finding a perfectly balanced house of cards in the middle of a hurricane. Researchers double-checked, then triple-checked their data, reanalyzing every pixel of imagery and every curve of the spectral data. The confirmation was undeniable. They had found a gravitational family of 14 stars, a system that defied conventional models and instantly became a laboratory for testing the extreme limits of celestial mechanics. This wasn't just a new discovery, it was a door swinging open to a universe far more bizarre and wonderful than we had ever imagined. Now, if you thought finding a family of 14 stars was mind-bending, wait until you learn how they're arranged. This isn't a simple, flat solar system like our own, with planets neatly orbiting a single central star. Instead, these systems are organized into what astronomers call extreme hierarchical orbits. Picture a set of Russian nesting dolls, but where each doll is a pair of stars spinning around each other. In a Quattuordecuple system, you have multiple levels of this gravitational choreography. At the most basic level, you have 2 stars locked in a tight, fast orbit around a common center of gravity. That's a binary pair. Then imagine two of these binary pairs, themselves separated by a greater distance, slowly circling one another. This creates a new, larger gravitational unit, but it doesn't stop there. Two of these quadruple systems might then orbit each other even farther out, forming an octuple system. In the most extreme cases, you can have several layers of this nesting, ultimately binding 14 individual stars into a single, coherent, yet incredibly complex gravitational dance. This layered structure is the only way such a system can remain stable. Without this careful ordering, the gravitational pulls would be chaotic and unpredictable, likely leading to stars being flung out into the void or crashing into one another in a cosmic catastrophe. This hierarchy imposes a delicate balance, a set of rules that allows for this incredible complexity to exist over astronomical timescales. What truly astonishes scientists is the sheer scale of these orbits. The innermost binary pairs might complete a full orbit in a matter of days, whipping around each other at incredible speeds. The next level out, where two binaries circle each other, could take years or even centuries to complete a single loop. And the outermost orbits, those that bind the entire system together, might have periods lasting thousands of years. This means that for some of these grand, sweeping orbital paths, human civilization hasn't even existed long enough to witness a full cycle. We're seeing just a single frame of a movie that is epochs long. This layered stability is a brilliant natural solution to a problem of cosmic proportions, but it creates another layer of mystery for us to unravel. This profound stability is perhaps the single greatest puzzle these systems present. Every simulation, every computer model based on our current understanding of gravity, predicted that a gathering of 14 massive objects in such close quarters should be a recipe for immediate and violent disaster. The gravitational forces at play should tug and pull at each other in unpredictable ways, leading to catastrophic collisions or stars being unceremoniously ejected into the darkness of interstellar space within a relatively short amount of time, cosmically speaking. The fact that we observe these systems not just existing but apparently thriving over millions of years forces us to confront a glaring gap in our knowledge. It's a cosmic paradox that has physicists both bewildered and utterly fascinated. The leading theory to explain this unexpected piece involves a delicate and rare phenomenon known as resonant orbits. Think of it like a perfectly timed musical round, where each voice enters at precisely the right moment to create a harmonious whole instead of a jumbled mess. In a gravitational resonance, the orbital periods of the different stellar pairs are locked into a precise mathematical ratio. For example, the time it takes for one inner binary to complete 3 orbits might exactly equal the time it takes for a wider pair to complete 2 orbits. This synchronicity means their gravitational interactions become predictable and rhythmic rather than chaotic. Instead of giving each other random, disruptive pulls, they give gentle, periodic tugs that actually help to maintain the system's balance, effectively canceling out the destabilizing forces over the long term. Another critical factor is the sheer, mind-boggling scale of the distances involved. While we call it a single system, the individual stars and their tight binary pairs are often separated by trillions of miles. To put that in perspective, the entire orbit of Pluto in our solar system could easily fit within the empty space between some of these stellar components. This immense breathing room drastically reduces the frequency of their gravitational interactions. They influence each other just enough to stay bound as a family, but they are so far apart that their encounters are gentle and gradual, like distant relatives who only meet on major holidays. This wide separation provides the stability that a more compact arrangement could never achieve. Scientists are now reworking their models to account for these newfound principles, suggesting that our universe has a natural preference for order, even in the most extreme environments. The existence of stable Quattuordecuple systems hints at a hidden set of rules governing complex gravitational dynamics, rules we are only beginning to decipher. Each stable system we find is a natural laboratory, offering a unique window into how gravity operates on a grand scale, pushing the boundaries of physics and compelling us to rethink what is possible in the cosmos. Yet for all their apparent stability, these intricate celestial families are not always peaceful. The same complex gravitational forces that can lock a system into a harmonious resonance can also, under the right conditions, turn it into the most powerful slingshot in the galaxy. While many of these 14 star systems achieve a delicate balance, others are caught in a moment of cosmic realignment, and the result is both violent and spectacular. Astronomers have directly observed the aftermath of these events, stars being hurled out of their birth systems at unimaginable speeds, becoming lone wanderers on a one-way trip through the void. These aren't gentle ejections, they are catastrophic gravitational kicks, a fundamental process that shapes not only the system left behind but the entire galaxy these runaway stars traverse. The mechanism behind this incredible phenomenon is known as a gravitational slingshot, a three-body interaction scaled up to an extreme degree. Imagine a close encounter between three stars within the system's crowded inner regions. As they swing past one another, their gravitational fields interact in a complex dance. Through this interaction, one star can absorb the orbital energy of the others, accelerating to a tremendous velocity while the other two stars sink closer together, tightening their own bond. The speeding star isn't just nudged, it is catapulted with such force that it achieves escape velocity, breaking free from the gravitational hold of its entire family forever. In a Quattuordecuple system, with so many massive objects moving in concert, the opportunities for these chaotic interactions are magnified, creating a perfect factory for these hypervelocity ejections. The stars that result from this process are known as hypervelocity stars, and they live up to their name. They are some of the fastest-moving objects in our galaxy, racing through space at speeds that can exceed 1,000,000 miles per hour. At that velocity, a star is no longer bound by the gravity of the Milky Way itself. It is on an intergalactic trajectory, destined to leave our galaxy and sail off into the vast, empty space between galaxies. These are not subtle changes in orbit. These are life-altering events for the star itself, and a dramatic loss of mass and energy for the system it left behind. The ejection acts as a pressure release valve, removing the destabilizing element and often allowing the remaining 13 stars to settle into a new, more stable configuration. The discovery of these hypervelocity stars provided some of the first indirect evidence for the existence of such complex systems long before we could directly image them. Astronomers would spot a solitary star moving in a direction and at a speed that defied all explanation, its trajectory a straight line pointing directly back to a distant region of the galaxy. By tracing these cosmic breadcrumbs backwards, they could often pinpoint the likely culprit, a dense, complex star system, a place where gravitational chaos could forge the fastest natural projectiles we have ever observed. This process reveals a universe in constant flux, where even the most seemingly stable arrangements are capable of sudden, violent, and beautiful change. If the very existence of these 14 star systems is a cosmic miracle, then the next discovery is nothing short of a revolution in planetary science. For decades, a fundamental rule of planet formation was that it required a calm, quiet nursery. A lone star with a vast, rotating disk of gas and dust gently coalescing over millions of years into worlds, free from violent gravitational interference. The chaotic gravitational environment of a multi-star system was thought to be a complete deal-breaker, a place where any budding clumps of matter would be instantly torn apart by incessant tidal forces. That is, until we looked closer at a Quattuordecuple system and found the impossible, robust, swirling protoplanetary disks orbiting individual stars within the chaos. This discovery turned planetary formation theory on its head. We now have direct observational evidence from systems like this showing not just one, but multiple distinct disks, each circling a different star within the larger gravitational family. These aren't faint, wispy things. They are massive, dense structures packed with enough material to form entire solar systems of their own. The presence of these disks forces us to ask a startling question. How can such delicate structures possibly survive and even thrive in what is essentially a perpetual gravitational hurricane? The answer seems to lie in that same hierarchical structure that stabilizes the stars themselves. A protoplanetary disk is safest when it is orbiting very closely to its host star. Within a certain distance, the parent star's gravity dominates so completely that it effectively shields the disk from the disruptive tugs of its many stellar siblings. It creates a gravitational bubble of relative calm, a small pocket of order within the overarching chaos. The disk is so close to its star that the complex dance happening between the other 13 stars becomes a distant, gentle pull, more like the moon's effect on Earth's oceans than a world-shattering force. This allows the basic processes of planet formation, dust grains sticking together, clumping into larger rocks, and eventually snowballing into planetesimals to begin. But the real shock came when astronomers detected not just disks, but the planetesimals themselves. Using advanced radio telescopes to peer into the dusty veil of these disks, they found telltale signs of objects several miles wide already coalescing. This means the building blocks of planets are actively forming right now in these extreme environments. It suggests that planets, perhaps even entire families of planets, could be born into a sky filled not with one sun, but with 13 others, each a brilliant point of light. The variety of worlds that could emerge from such a birthplace is staggering to contemplate. Imagine a planet forming in the habitable zone of one star in this system. Its year would be defined by its orbit around its sun, but its heavens would be a spectacle unlike any other. Multiple suns of varying colors and brightness would hang in its sky, some locked in a perpetual dance with each other, others rising and setting over cycles lasting centuries. The gravitational influences from these other stars would inevitably tug and sculpt the outer reaches of that planet's solar system, likely creating bizarre, elongated orbits for any comets or dwarf planets in its outer confines. The very notion of a stable, predictable orbital environment is completely rewritten. This discovery doesn't just add a new chapter to planet formation. It opens up an entirely new volume on the potential diversity of worlds in our galaxy, proving that planets can form in places we once thought were utterly hopeless. And just when we thought the dynamics of these systems couldn't get any more extreme, we encounter the true survivors of the cosmic ballet, the stellar phoenixes that have literally died and come back. Within the tangled gravitational web of a Quattuordecuple system, astronomers have made a truly ghostly discovery: the remains of stars that have undergone the most violent death possible, a supernova explosion, yet somehow never left the family. These are white dwarfs and neutron stars, the incredibly dense cores left behind after a star exhausts its fuel and blows its outer layers into space. They are the zombie stars, dead but still active, gravitationally bound to their living siblings despite having literally exploded. The existence of these objects defies all intuition. A supernova is one of the most energetic events in the universe, releasing in a single instant the amount of energy our Sun will produce over its entire 10 billion-year lifetime. This explosion is so powerful it can outshine an entire galaxy of stars. Logic would dictate that such a cataclysmic event, happening right in the heart of a complex gravitational system, would be the ultimate deal-breaker. The sudden, asymmetric loss of a huge amount of mass and the immense shockwave should act like a bomb going off in a carefully arranged house of cards, instantly destabilizing the orbits of every other star and likely ejecting several of them into deep space. The fact that we find these dense remnants still neatly integrated into the orbital hierarchy means the system somehow weathered the storm. So how does a star system survive a supernova? The secret appears to lie in the incredible distances between the stellar components we discussed earlier. Remember, these stars are separated by trillions of miles. While the supernova is unfathomably bright and violent, its most disruptive effect, the instantaneous loss of a significant portion of the dying star's mass, happens very close to the star itself. From the perspective of a sibling star light years away, the event is more of a gradual change in the gravitational landscape than a sudden shock. The mass loss means the gravitational glue holding that particular part of the system together weakens significantly, but it doesn't vanish all at once. The other stars experience this as a gentle relaxing of the pull, allowing their orbits to widen and adjust gradually rather than being violently snapped. Furthermore, if the supernova explosion is perfectly symmetrical, a possibility for some types of stellar deaths, the kick from the blast, can be minimized. An asymmetric explosion would give the resulting neutron star or white dwarf a massive kick velocity, shooting it through the system like a bullet and almost certainly ejecting it. But a symmetric explosion allows the dead core to remain almost exactly where it was, its gravitational influence now reduced but still present. The system's intricate hierarchical structure then does the rest of the work, with the wider orbits providing a buffer that absorbs the change over millennia, allowing the entire family to recalibrate and find a new stable configuration with their deceased relatives still at the dance. This discovery provides astronomers with a rare and valuable opportunity. These zombie stars are cosmic clocks and history books. By studying their properties, their mass, spin, and composition, scientists can work backwards to determine the properties of the original star that died, a star we can never directly observe. Its death also likely seeded the surrounding protoplanetary disks we talked about, with heavy elements like gold, platinum, and uranium, enriching any future planets that may form. The presence of a neutron star, in particular, can dramatically influence the system, as its intense magnetic fields and radiation can sterilize nearby space or, conversely, trigger new waves of star formation in surrounding gas clouds. A dead star in a Quattuordecuple system is far from a silent relic. It is an active and powerful architect, continuing to shape its extraordinary family from beyond the grave. If the intricate hierarchy of these systems provides a framework for stability, then the next discovery reveals the chaotic fingerprints of their violent birth. We tend to imagine star systems forming from a single, calmly spinning cloud of gas and dust, flattening into a neat disk where everything orbits in the same plane, much like our own solar system. But Quattuordecuple systems laugh in the face of that orderly picture. Astronomers have measured the orbital planes of the different binary pairs within these 14 star families and found something astonishing. They are often wildly tilted, sometimes even perpendicular or fully counter-rotating relative to one another. This isn't a flat, organized structure. It's a three-dimensional tangle of orbits, a celestial game of pick-up sticks frozen in motion. This profound misalignment is a glaring clue that these systems did not form from the peaceful collapse of one solitary nebula. Instead, it points to a far more dramatic and violent origin story, a celestial demolition derby that occurred in a densely packed stellar nursery. The leading theory suggests that what we are seeing is the aftermath of a gravitational takeover, a grand merger of several smaller, pre-existing star systems that wandered too close to one another in the chaotic environment of a young star cluster. Each of these smaller systems, perhaps a triple here, a binary there would have formed with its own distinct orbital orientation, its own unique tilt based on the random motions of the gas cloud it condensed from. Billions of years ago, these independent families were drifting through space when their gravitational fields began to interact. They were slowly drawn together, not in a head-on collision, but in a complex gravitational capture. As they intertwined, they didn't have the time or the energy to realign all their orbits into a single new plane. the system instead found a stable, albeit immensely complex, configuration that preserved much of the original orbital memory of each captured group. The result is a fossil record of this ancient encounter, a cosmic collage where the distinct tilts of each subgroup tell the story of their separate origins before they were forcibly joined together. This chaotic formation mechanism helps explain another layer of their unlikely stability. A system that forms from a single cloud has one unified angular momentum, a single direction of spin that everything must follow. But a system built from multiple captured groups has numerous competing momentums that essentially cancel each other out on a grand scale. This can actually suppress large-scale gravitational instabilities that would otherwise tear the family apart. The very chaos of its birth becomes the key to its long-term survival, creating a delicate balance of opposing forces that allows 14 stars to coexist in a stable, if wildly misaligned, gravitational dance. The chaos we observe within these systems is not always contained. For all their intricate internal stability, some quattuordecuple systems are engaged in a far grander and more dramatic motion. They are fleeing. Astronomers have tracked a number of these 14 star families and discovered something that at first seems impossible. They are not merely drifting along with the general rotation of the Milky Way galaxy. They are moving through it at astonishing speeds on radically different trajectories from the stars around them. These are what scientists call high peculiar velocity systems, and their breakneck pace tells a story of a violent expulsion from their birthplace millions of years ago. To understand this, picture the dense, chaotic environment of a young star cluster, the stellar nursery where these systems are born. It's a crowded metropolitan area of stars with massive celestial bodies constantly brushing past one another, their gravitational fields interacting in complex ways. In such a crowded neighborhood, a gravitational showdown between two incredibly massive systems is inevitable. Imagine a quattuordecuple system, itself a gravitational titan, having a close encounter with another behemoth, perhaps an even larger star system or a mid-sized black hole. The gravitational forces between them are immense. This interaction is not a slow dance, it's a slingshot effect on a galactic scale. As the two massive objects swing past each other, the quattuordecuple system can be flung away at an incredible velocity, like a stone launched from a sling. The energy for this tremendous kick comes from the orbital energy of the two interacting bodies themselves. The runaway system is ejected from the cluster entirely, cast out into the lonely expanse of the galactic disk, while the other object involved in the interaction settles into a tighter, lower-energy orbit within the cluster. This process essentially uses the gravitational potential of the cluster as a giant cannon. The evidence for this is written in their motion. By measuring the system's velocity vector, both its speed and direction, astronomers can often trace a straight line backwards directly to a specific, dense star cluster, the likely scene of the crime. These runaways are cosmic fugitives, and their speed is their most telling feature. They can be hurtling through space at hundreds of kilometers per second, a pace so relentless that they will eventually break free from the gravitational pull of their birth cluster and even alter their path through the galaxy itself. They become isolated island universes, carrying their complex internal order with them on a high-speed journey through the void, a permanent testament to a dramatic gravitational encounter that occurred eons ago. These complex interactions of gravity and motion give rise to one of the most visually spectacular features found in these systems: vast, ethereal bridges of matter known as tidal tails. Imagine not just stars orbiting each other, but being connected by luminous, streamer-like structures of gas and dust that stretch across trillions of miles of space. These are not solid structures, but rather beautiful, chaotic cosmic ribbons, the visible evidence of the immense gravitational forces constantly at work, pulling and stretching material between the stellar companions. These tidal tails form through a process of relentless gravitational tug-of-war. When two stars, or even two tightly bound binary pairs, make a close pass in their wide orbits, their gravity doesn't just affect their paths, it violently distorts their very forms. For stars with expansive atmospheres, especially younger, more volatile ones, this can pull huge plumes of stellar material out into space. But the most dramatic tales are born from the protoplanetary disks we discussed earlier. These vast, rotating clouds of gas and dust are far more loosely bound than a star itself, making them incredibly vulnerable to gravitational theft. As a star with its disk swings past a nearby stellar sibling, the sibling's gravity acts like a colossal hand, reaching in and grabbing the outermost, most tenuous material of the disk. It doesn't just pull it away in a single clump. It stretches it, shearing it into a long, streamer-like filament that points directly toward the gravitational culprit. Because these stars are in constant motion, this process doesn't happen just once. With each close encounter, more material is siphoned off, creating an intricate web of these tidal streams that connect various members of the 14-star family, a permanent record of their gravitational interactions over millennia. The composition of these tales is a treasure trove for astronomers. They are not empty, they are filled with gas, dust, and critically, complex molecules and ices that are the very precursors to life. As this material is stretched out into the relative cold and quiet of space between the stars, shielded from the intense radiation of their surfaces, these molecules have a chance to combine and form even more complex compounds. These cosmic ribbons effectively become sprawling chemistry labs, factories for organic molecules that are then scattered throughout the system, potentially seeding any forming planets with the basic ingredients for biology. In a sense, these tidal tails are the system's circulatory system. They are not just one-way streets of lost material. While much of the gas and dust is lost forever to interstellar space, some of it can be captured by the gravity of the other star, funneling fresh material onto its own disk or even directly onto its surface. This transfer of mass can influence the evolution of the stars involved, providing new fuel for one while starving another. They represent a continuous, dynamic exchange of matter, a literal flow of cosmic building blocks that intertwines the fates of all 14 stars in a way that is both destructive and creatively fertile. The extreme environment of a Quattuordecuple star system doesn't just create bizarre orbits, it acts as a forge for some of the rarest and most peculiar star types in the universe. Within these dense stellar families, astronomers have identified stellar oddities that are vanishingly rare in more solitary environments, each one a direct product of the complex gravitational interactions constantly at play. These aren't your average main sequence stars, they are cosmic chimeras, their very forms and functions altered by the intense conditions of their birthplace. Chief among these exotic specimens are stars known as blue stragglers. Picture a star cluster where all the massive, hot, blue stars burned out billions of years ago, leaving behind only their smaller, cooler, redder siblings. A blue straggler is a brilliant, hot, blue star that stands out in this elderly crowd, seemingly defying the laws of stellar evolution by appearing young long after its generation should have died. In a Quattuordecuple system, their origin becomes clear. The crowded conditions make direct stellar collisions or near misses startlingly common. Two older, lower mass stars can be gravitationally forced into a merger, combining their fuel to create a single, massive, hot star that looks brand new. It's a stellar resurrection, a phoenix born not from fire, but from a violent gravitational embrace. Another fascinating product of this environment is the B star. These are not just hot, massive stars, they are rapid spinners, rotating so fast that they fling their own material out into space, forming a distinctive, dense equatorial disk of gas that encircles them like a cosmic hula hoop. While B stars exist elsewhere, their frequency in complex systems suggests the gravitational nudges from numerous siblings are a primary trigger. A close pass from another star can transfer angular momentum, spinning up a star like a top and initiating the process of disk formation. This makes these systems prolific factories for B stars, their chaotic dances literally shaping the stars themselves. Perhaps the most chemically unusual stars found here are the magnetic chemically peculiar stars, or AP/BP stars. Their surfaces are not a uniform mix of elements. Instead, they exhibit bizarre, patchy concentrations of rare elements like silicon, chromium, europium, and even precious metals like gold and platinum. These strange surface maps are believed to be caused by incredibly powerful magnetic fields that trap heavier elements, preventing them from sinking down into the star's interior. The turbulent history of a Quattuordecuple system, potentially enriched by material from a past supernova explosion within the family, provides an abundant supply of these heavy elements. The complex gravitational environment then likely plays a role in amplifying the star's magnetic field, creating the perfect conditions for these stellar chemical factories to form. Each of these exotic stars is more than just a curiosity. They are active participants in the system's ecology. The intense ultraviolet radiation from a blue straggler can heat the protoplanetary disks around other stars, influencing the types of chemistry and planets that can form there. The gaseous disk of a B star can be periodically stripped away by a close passing sibling, creating spectacular outbursts and transferring material across the system. The powerful magnetic fields of an AP star can carve out vast cavities in the surrounding interstellar medium. Their presence proves that in a Quattuordecuple system, the stars themselves are not passive inhabitants. They are constantly being remade and influenced by their extraordinary family, becoming living records of the system's dynamic and violent history. While the exotic stars and complex orbits paint a picture of cosmic grandeur, the reality of life within a Quattuordecuple system would be anything but tranquil. If a planet were to form in the habitable zone of one star, its inhabitants would live under a constant threat of celestial violence, witnessing a sky periodically torn apart by eruptions of energy so vast they defy comprehension. Astronomers monitoring these systems have detected a phenomenon that makes our sun's most powerful solar flares look like a mere spark, superflares. These are not just slightly larger versions of the flares we know. They are cataclysmic outbursts, releasing energy equivalent to billions of hydrogen bombs detonating at once, often from stars we would otherwise consider stable and calm. The root cause of these apocalyptic events lies in the same gravitational chaos that defines the system. Many of the stars in these tightly bound families are forced into incredibly fast rotations by the constant gravitational tugging from their siblings. Think of it like a figure skater pulling their arms in to spin faster. A close stellar pass can transfer angular momentum, causing a star to whip around on its axis at a dizzying pace. This rapid spin acts as a dynamo, twisting and amplifying the star's magnetic field to incredible strengths, far beyond anything our sun possesses. These magnetic fields become tangled and stressed, storing immense amounts of energy like a coiled spring. Eventually, the tension becomes too great and the field lines snap, reconnecting in a fraction of a second. This magnetic reconnection is the trigger, unleashing all that pent-up energy in a single, devastating burst across the entire electromagnetic spectrum. The effects of such a superflare on any nearby planets would be nothing short of an extinction-level event. The initial flash of X-rays and ultraviolet radiation would arrive at the speed of light, instantly stripping away the ozone layer of an Earth-like world and bathing its surface in lethal mutagenic radiation. This would be followed hours or days later by a torrent of high-energy protons, a coronal mass ejection moving at a significant fraction of light speed. This onslaught would scour the planet's surface, destroying atmospheres and evaporating oceans, effectively sterilizing any world unfortunate enough to lie in the path of the blast. For a planet orbiting a flare star in this system, the concept of a stable climate or a safe environment for life to evolve would be a cosmic joke. Yet, paradoxically, this same violent mechanism might also play a role in sparking the very chemistry needed for life. The intense ultraviolet radiation from these flares, while destructive on a planetary scale, is a powerful catalyst in the vast molecular clouds of the protoplanetary disks. It can break apart simple molecules, allowing the atoms to recombine into more complex organic compounds, the precursors to amino acids and sugars, in the dense, shielded regions of a disk far from the surface of a vulnerable planet. These superflares could be driving a frantic pace of probiotic chemistry, literally forging the building blocks of life in chaotic bursts of energy. It's a dramatic double-edged sword. The same event that can sterilize a world might also be enriching its birth cloud with the essential ingredients for biology, setting the stage for life to begin again once the stellar fury has subsided. But the ultimate expression of this gravitational sculpting is the creation of a fully warped disk. Instead of a simple, clean tilt, the entire disk can be twisted like a vinyl record left in the sun, with the inner regions orbiting in one plane and the outer regions being progressively dragged into an entirely different orientation by the dominant pull of a passing stellar sibling. This creates a disk that is fundamentally non-planar, a three-dimensional spiral of dust and gas that defies our basic models of how these structures form and evolve. Observing such a warped disk is like finding a phonograph record that's been melted and sculpted into a spiral staircase. It's a direct, visible record of the relentless gravitational forces that have been acting upon it for millennia. The consequences of this warping and truncation are profound for any potential planets trying to form within these distorted nurseries. The process of planet formation relies on a calm, settled environment where dust grains can gently collide and stick together, gradually building up into planetesimals and eventually planets. A warped or truncated disk is the antithesis of this calm. The severe changes in density and temperature across the disk create turbulent, hostile zones where growing clumps of matter are more likely to be shattered in collisions than to gently coalesce. It suggests that planet formation in such an extreme environment would be a stop-start chaotic process, potentially producing a population of planets on wildly eccentric and inclined orbits if they can form at all. Yet, for all the chaos they represent, these warped disks are also cosmic laboratories. They allow us to observe and model gravitational interactions with a precision that would be impossible anywhere else. By meticulously mapping the exact shape of a warped disk, how severely it's tilted, where the truncation radius lies, astronomers can work backwards. They can calculate the mass, orbit, and even the history of the perturbing stars that caused the damage, turning the disk itself into a sensitive gravitational instrument that reveals the secrets of the entire system. This bizarre distortion, a sign of violence and chaos, ultimately becomes one of our most valuable tools for understanding the intricate dance of 14 stars. Even with 14 brilliant suns illuminating a quattuordecuple system, astronomers are often left with the unsettling feeling that something massive is hiding in the shadows. This brings us to one of the most intriguing cosmic detective stories unfolding in these systems, the case of the missing mass. When scientists meticulously chart the orbits of all the visible stars, applying the immutable laws of gravity, they often encounter a glaring discrepancy. The mathematics simply don't add up. The stars are moving in ways that suggest they are feeling the gravitational pull of far more material than what is visible to our telescopes. It's as if every time we count the dancers in the ballroom, the music suggests there are several more invisible partners guiding the steps from the darkness. This isn't a small accounting error. It's a fundamental problem that points to the presence of dark, massive objects woven into the fabric of the system itself. The orbital periods, the subtle wobbles, the precise angles of the paths, all of it serves as evidence in a gravitational courtroom. The visible stars are behaving like witnesses whose testimony only makes sense if we infer the existence of another, unseen entity influencing them. This discrepancy forces a startling conclusion. Our census of the system is incomplete. beyond the 14 stars we can see, there must be additional massive bodies whose gravity is essential to maintaining the delicate balance we observe. The prime suspects in this cosmic mystery are some of the most elusive objects in the universe. At the top of the list are black holes. A stellar mass black hole, the remnant of a massive star that collapsed without the fireworks of a supernova, would be a perfect candidate. It would possess tremendous gravitational influence, yet emit no light of its own, making it virtually undetectable except through its pull on its stellar neighbors. Another compelling suspect is a brown dwarf, a failed star that never gathered enough mass to ignite sustained hydrogen fusion. These objects can be dozens of times more massive than Jupiter, but glow only faintly with residual infrared heat, easily lost in the blinding glare of 14 brilliant suns. Even a large, dense planet, a so-called super-Jupiter roaming freely in the outer reaches, could account for some of the anomalous motions. The hunt for these dark companions is a painstaking process of elimination and inference. Astronomers build incredibly complex computer models of the system, inputting the precise masses, positions, and velocities of every known star. They then set the simulation in motion, watching to see if the virtual system remains stable over millions of simulated years or if it flies apart. More often than not, the model only achieves long-term stability when they add the gravitational influence of one or more unseen masses in specific orbits. It's a process of reverse engineering the system's stability, using the laws of physics to tell us what must be there, even if our eyes cannot yet see it. This missing mass problem profoundly connects these rare 14-star systems to one of the greatest mysteries in all of cosmology: the nature of dark matter. While the hidden mass here is likely made of ordinary baryonic matter, stuff like protons and neutrons in black holes and brown dwarfs, the investigative technique is eerily similar. Just as we infer the presence of dark matter halos around galaxies by observing the orbits of stars, we are now inferring the presence of dark companions within star systems by observing the orbits of their suns. It demonstrates that the universe is filled with influences we cannot see, from the smallest stellar system to the largest galactic cluster. Each Quattuordecuple system with missing mass is a miniature laboratory, offering us a chance to practice the delicate art of weighing the invisible and to remind ourselves that what we see is only a small fraction of what is truly there. If you thought the gravitational dynamics of these systems were complex, wait until you peer into their very chemistry. Spectroscopic analysis, which allows astronomers to dissect the light from a star to reveal its elemental composition, has uncovered a bizarre chemical fingerprint in many of these 14 sun families. The atmospheres of these stars aren't showing the standard cosmic recipe of hydrogen and helium with a sprinkling of heavier elements. Instead, they're sporting dramatic and peculiar overabundances of specific, often rare, elements. We're talking about stars with surfaces bizarrely rich in lithium, an element usually destroyed early in a star's life, or gleaming with unexpected concentrations of heavy metals like strontium, barium, and even europium. This isn't a natural stellar composition. It's the sign of a star that has been chemically polluted, its pristine atmosphere contaminated by material that was never its own. The most likely culprit for this cosmic contamination is a process known as mass transfer, a stellar heist occurring right before our eyes. In a system with so many stars in such close gravitational proximity, the outer atmospheres of evolved stars can literally spill over onto their companions. Imagine a star like a red giant, bloated and nearing the end of its life. Its outer layers are loosely bound, a glowing, tenuous cloud of gas. If this star has a close binary partner, the gravitational pull from that companion can act like a siphon, pulling this stellar material across the space between them and onto its own surface. The donor star is slowly cannibalized, while the recipient star gains not just mass, but an entirely new chemical identity, its atmosphere now laced with the fused elements from the interior of its dying sibling. This transferred material is the processed ash of nuclear fusion, carrying the unique signature of elements forged deep within the donor star's core. Elements like barium and strontium are produced through complex nuclear processes like the slow neutron capture process, which occurs in the intense environments of aging giant stars. When this enriched material is dumped onto the surface of an otherwise normal star, it creates a glaring chemical anomaly, a star that looks young and hot on the outside but has the atmospheric chemistry of a star in its old age. It's a form of stellar identity theft where one star's interior becomes another star's exterior, permanently recording the history of their intimate gravitational relationship. But mass transfer isn't the only polluter in this crowded neighborhood. The fierce stellar winds blowing from massive, hot stars also play a critical role. These aren't gentle breezes, they are hurricane-force outflows of particles carrying tiny amounts of the star's own surface material out into space. In a densely packed system, these winds don't just dissipate into the void. They can directly blast onto the surfaces of nearby stellar siblings, dusting them with a faint but measurable layer of foreign elements. Over millions of years, this continuous sandblasting of stellar material can significantly alter the chemical makeup of a star's observable layers, creating another pathway for chemical peculiarity. The winds act as a communal exchange program, ensuring that no star in the system is an isolated chemical island. They are all sharing, stealing, and swapping material in a continuous cosmic cycle. The presence of these chemical anomalies is far more than just a curious detail. It's a powerful forensic tool. For astronomers, a star with a lithium-rich surface or an overabundance of heavy metals is like finding a distinct fingerprint at a crime scene. It provides irrefutable evidence of a past interaction, a direct tag that tells us this star has a history of gravitational intimacy with a companion. By studying the specific mix of elements, scientists can even work backwards to determine what type of star was the original polluter, whether it was a red giant, a massive star, or something else entirely. This turns each chemically peculiar star into a living history book, its atmosphere recording events that may have occurred billions of years ago, preserving the story of the system's dynamic and interactive past in a way that orbital mechanics alone never could. This brings us to one of the most head-scratching discoveries in these systems, a finding that seems to break a fundamental rule of stellar astronomy. When you look at a star cluster, you expect all the stars to be roughly the same age. They were all born from the same cloud of gas and dust at the same cosmic moment. But within a single Quattuordecuple system, astronomers are finding stars that tell wildly different stories about their age. Some members appear as ancient, cooler red giants, bloated and nearing the end of their long lives, while their siblings look like vibrant, hot blue teenagers blazing with youthful energy. It's like walking into a family reunion and finding great-grandparents standing next to their great-grandchildren, with no middle generations in sight. This bizarre age gap isn't just a visual trick, it's a direct challenge to our understanding of how stars are born and evolve together. The most dramatic explanation for this cosmic age paradox is a phenomenon known as stellar rejuvenation. This isn't about stars finding a cosmic fountain of youth. It's a violent and transformative process of theft and merger. The youthful-looking blue stragglers we discussed earlier are the prime suspects here. These stars only appear young because they have been fundamentally remade. The chaotic gravitational environment of a 14-star system makes stellar collisions and near misses startlingly common. When two older, lower-mass stars are forced together, either through a direct collision or by spiraling into each other in a tight binary merger, their fuel is combined. The result is a single, new, more massive star. This new star has a fresh supply of hydrogen fuel at its core, allowing it to burn hotter and brighter, effectively resetting its evolutionary clock. It's not actually younger, but it has the characteristics of a much younger star, creating a glaring discrepancy right next to its unaltered, aging siblings. Another powerful rejuvenation mechanism is mass transfer, a slower but equally effective form of stellar theft. In a close binary pair, one star might evolve faster than its partner, swelling into a red giant. As it expands, its outer layers become gravitationally vulnerable. The companion star can then siphon off this hydrogen-rich material, pulling it onto its own surface. The recipient star gains a new layer of fresh fuel, causing it to brighten and heat up, mimicking the appearance of a star in its prime. The donor star, meanwhile, is left stripped down to its exposed, helium-rich core, appearing much older and more evolved than it truly is. This process creates a bizarre pair, one star that looks artificially young and vigorous, and another that looks prematurely ancient and depleted, all from the same original birth cloud. But stellar mergers and mass transfer aren't the only culprits. The chaotic formation history of these systems also plays a role. The prevailing theory suggests that a Quattuordecuple system isn't born in a single, tranquil event. It's more likely assembled over time through a series of gravitational captures where smaller pre-existing systems, each with their own slight age differences, are drawn together and locked into a new, larger family. A triple system that formed a few million years after a binary system might be captured by it. While a few million years is a blink of an eye on the cosmic scale, it is enough time for the most massive stars in the older group to have already evolved into giants or supergiants, while the stars in the slightly younger captured group are still on the main sequence. This would create a system where the stars have nearly identical ages, but their evolutionary states are drastically out of sync, presenting a confusing picture to observers. Untangling this mystery requires astronomers to act like cosmic detectives, using multiple lines of evidence to piece together the true history. They don't just look at a star's color and temperature, they perform a detailed chemical autopsy. A star that has been rejuvenated by mass transfer will often have a very specific chemical signature on its surface. An overabundance of elements like carbon, nitrogen, and barium that are normally forged deep in the core of an evolved giant star. Finding those elements on the surface of a hot, blue star is the smoking gun, proving it was polluted by material from a companion. Conversely, if the stars show different chemical compositions that suggest they formed in separate molecular clouds altogether, it points strongly to the capture theory. Each chemically peculiar star becomes a living history book, its atmosphere recording the violent and interactive events that have defined the system's long and complex life. Amidst the apparent chaos of 14 stars whirling through space, astronomers have uncovered a hidden order so precise it borders on the musical. This discovery revolves around the phenomenon of resonant orbital locking, where the complex dance of the stars is governed not by randomness but by a delicate mathematical harmony. By meticulously tracking the orbital periods of the various binary pairs within these systems, scientists found that their cycles are not independent. Instead, they are often locked together in simple, perfect integer ratios. You might find one tight binary pair that completes exactly 3 orbits in the same time a wider pair completes 2, a clean 3-to-2 resonance. Another might exhibit a 2-to-1 ratio or a 4-to-3. This isn't a coincidence, it's a fundamental mechanism of stability, a gravitational symphony playing out over eons. This resonance works like a perfectly timed push on a child's swing. If you push at just the right moment in the swing's arc, you add energy efficiently and maintain a smooth, high motion. Push at the wrong time and you disrupt the rhythm, causing a jerky, unstable ride. In a resonant star system, the gravitational pull between pairs acts like that perfectly timed push. When the stars align at specific points in their orbits, their periastron, or closest approach, the gravitational tug they exert on each other is rhythmic and reinforcing. These periodic, gentle kicks serve to keep their orbits stable and predictable, preventing the gradual drift into chaos that would otherwise be inevitable. The resonance effectively cancels out the accumulating tiny perturbations, creating a fragile, self-correcting balance. The music analogy is almost literal. These integer ratios are the same simple fractions that form the foundation of musical harmony. A 2-to-1 orbital resonance is the gravitational equivalent of a musical octave, where one note vibrates exactly twice as fast as another. A 3-to-2 resonance mirrors a perfect fifth, one of the most stable and pleasing intervals in music. This discovery suggests that the same mathematical principles that bring order to sound can also bring order to the universe's most complex gravitational arrangements. It's a cosmic melody with the stars themselves as the instruments, their orbits creating a harmony that is both beautiful and functionally essential for their long-term survival. Finding these resonances was a triumph of long-term observation and computational modeling. Astronomers had to gather years, sometimes decades, of precise positional data to even begin to calculate the orbital periods with enough accuracy to detect these subtle relationships. They then ran thousands of computer simulations, starting with random orbital configurations, and found that only those systems that naturally fell into resonant locks managed to persist for astronomical timescales. The others quickly flew apart. This confirmed that resonance isn't just a curious feature, it is likely a prerequisite for the very existence of such extreme systems. They can only form and survive if they can find these harmonious grooves in the fabric of space-time. Yet for all its stabilizing power, this harmony is incredibly fragile. It's a balance that exists on a knife's edge. The introduction of any significant external force, a close pass by another star cluster, or the gravitational influence of a hidden black hole could disrupt the precise timing of these gravitational pushes. If the rhythm is thrown off even slightly, the resonant lock can break. The stabilizing pushes become disruptive shoves, and the entire system can rapidly descend into chaos, potentially ejecting stars or triggering catastrophic collisions. The persistence of these systems is a testament to the quiet, isolated regions of space they often inhabit, where they can perform their intricate ballet undisturbed for millions of years. This delicate interplay between order and chaos, between musical harmony and gravitational catastrophe, defines the breathtakingly precarious existence of a Quattuordecuple star system. Moving from the musical harmony of resonances, we encounter a configuration so perfectly balanced it seems almost engineered, the stellar equivalent of a Trojan horse, but in this case it's a star acting as the hidden passenger. Astronomers have observed a breathtaking arrangement within some of these complex systems where a smaller star, or even an entire binary pair, is found orbiting not a single star but a point in empty space. This isn't a random placement, it's locked into one of the system's gravitational sweet spots, a Lagrange point, creating a stable stellar configuration that mirrors the Trojan asteroid sharing Jupiter's orbit around our Sun. To understand how this works, picture a massive binary pair, two stars locked in a tight, mutual orbit. As they circle each other, there are 5 specific points in their combined gravitational field where the pulls from the two stars and the centrifugal force of orbiting their center of mass perfectly cancel each other out. These are the Lagrange points, regions of equilibrium where a smaller object can theoretically park itself and remain stable. The most stable of these points, known as L4 and L5, lie 60 degrees ahead of and behind the smaller star in its orbit. It is at these precise locations that astronomers have found actual stars or smaller binaries peacefully coexisting, trapped in a gravitational embrace that allows them to share an orbital path with a far more massive pair. The stability of this Trojan configuration is a delicate miracle. The smaller star is essentially surfing the gravitational wave created by the massive binary ahead of it. Its own gravity is negligible compared to the giants it follows, so it doesn't disrupt their dance. Instead, it is gently shepherded along, forever maintaining its 60-degree lead or lag, tracing the same orbital path around the system's center of mass. This creates a spectacular and highly ordered celestial formation, with three distinct masses: the massive binary and the two Trojan stars at L4 and L5, constantly maintaining the same positions relative to each other, forming a gigantic, slowly rotating triangle in space that persists for millions of years. Discovering these stellar Trojans was a feat of precise measurement and patience. Astronomers had to track the motions of every component in the system with extreme accuracy over long periods to confirm that the smaller object wasn't just in a wide, independent orbit, but was truly locked into that specific gravitational null point. The confirmation of even one such configuration sent ripples through the astrophysics community, as it provided a stunning natural demonstration of celestial mechanics principles that were previously only theoretical on such a grand scale. It showed that the universe can assemble its most complex structures with a precision we are only beginning to appreciate, using the fundamental laws of physics as its blueprint. Tucked away within the gravitational whirlwind of these 14 star systems, astronomers have uncovered some of the most volatile relationships in the galaxy: pairs of stars locked in a deadly embrace, destined to erupt in violent outbursts of light. These are cataclysmic variable systems, and their discovery within a Quattuordecuple arrangement adds an entirely new layer of cosmic drama. At the heart of each of these binaries lies a white dwarf, the dense, Earth-sized corpse of a sun-like star. Its partner is typically a main sequence star, similar to our Sun, or a bloated red giant. They orbit each other so closely that their fates are inextricably linked by a relentless flow of stolen matter, a process that periodically triggers eruptions visible across interstellar distances. This theft of matter, known as accretion, is a direct consequence of their cramped quarters and the white dwarf's immense gravity. The companion star ventures too close, and the white dwarf's gravitational pull becomes overwhelming. It begins to strip material away from the outer layers of its victim, drawing the stolen gas into a swirling, superheated disk around itself. This accretion disk, spinning at a significant fraction of the speed of light, glows with fierce intensity as friction heats the gas to millions of degrees. But the disk is unstable. It's a reservoir of potential energy waiting for a trigger. When enough hydrogen-rich gas accumulates on the surface of the incredibly dense white dwarf, pressure and heat at the base of this layer reach a critical point, igniting runaway thermonuclear fusion. In a blinding flash, the accumulated hydrogen explodes in a colossal surface detonation, causing the entire system to brighten exponentially in a phenomenon we call a nova. The presence of such volatile pairs within an already chaotic 14-star system is a testament to the complex gravitational environment. The same gravitational nudges from stellar siblings that can create resonant harmony can also, over millennia, gradually alter the orbits of a wide binary pair, forcing them closer and closer together until they cross the threshold for this destructive interaction to begin. The larger system acts as a master puppeteer, orchestrating the conditions for these celestial time bombs to form and eventually ignite. This means that within the same family of stars, you can have the serene, resonant dance of wide binaries coexisting with the violent, intimate tango of a cataclysmic variable, all influencing each other through their shared gravity. For observers, the telltale signature of these systems is their wild, unpredictable flickering. Their light output is anything but steady. It can sit at a constant, elevated brightness for years, powered by the glowing accretion disk, and then, without warning, flare by a factor of 10,000 in a matter of hours as the nova explosion occurs, outshining every other star in the system combined before slowly fading back to its original state over weeks or months. This cycle can repeat every few decades or centuries as the white dwarf patiently begins siphoning fuel again for its next outburst. Each eruption seeds the surrounding system with the heavy elements forged in the blast, potentially enriching the protoplanetary disks of other stars within the family with new materials. The long-term fate of these cataclysmic variables is even more extreme. With every nova eruption, a tiny amount of mass is thought to be permanently added to the white dwarf. Over countless cycles, if it can accumulate enough mass to reach a critical threshold known as the Chandrasekhar limit, the entire white dwarf could face a far more final and catastrophic end. It would no longer be a surface explosion, but a complete thermonuclear detonation of the star itself, a Type Ia supernova. This event would be so powerful it could vaporize any nearby planets and severely disrupt the orbits of every other star in the Quattuordecuple system. The fact that we see these ticking time bombs actively accreting within these stable systems suggests that such a supernova may be a rare but inevitable outcome, a future cataclysm written into the very fabric of this extraordinary stellar family. For astronomers who dedicate their lives to studying variable stars, monitoring the light from a typical system usually involves tracking a steady, predictable rhythm. A binary pair might eclipse each other like clockwork every few days, or a pulsating star might swell and contract with metronomic regularity. But point your telescope at a Quattuordecuple system and you abandon all hope of predictability. The combined light from these 14 suns doesn't follow a rhythm. It writes a chaotic, unpredictable symphony of flickers, flares, and fades, creating a light curve so complex it can look more like a seismograph during an earthquake than a chart of stellar brightness. This erratic behavior is a nightmare for traditional classification, but an absolute delight for scientists seeking to understand the incredibly dynamic interactions happening in real time. The most predictable variations come from a phenomenon we're familiar with: eclipses. When one star in a tight binary pair passes in front of its companion from our vantage point on Earth, it causes a brief, symmetrical dip in the system's total light output. In a simple system, you get two distinct dips per orbit, but in a system with multiple eclipsing binaries, all contributing their overlapping cycles, the simple pattern explodes into a tangled web of dips. One binary might have a 3-day orbit causing dips every day and a half, while another pair in the same system eclipses every week. Their minima don't just add up, they interact. You might see a deep dip from one pair suddenly interrupted by a shallower dip from another, or a long, flat minimum when two eclipses happen to coincide perfectly. Untangling this mess requires isolating the light from each individual pair, a forensic task of incredible complexity. But the true chaos begins when you factor in the stars themselves, which are far from the steady, placid light sources we often imagine. Many of the stars in these systems are incredibly active, prone to the colossal superflares we discussed earlier. These aren't gradual brightenings, they are violent, stochastic eruptions that can cause the system's total brightness to spike by 10% or more in a matter of hours, completely overwriting the gentle pattern of the eclipses before fading away over several days. Imagine trying to listen to a soft melody while random, deafening cymbal crashes erupt without warning. That's the challenge of observing these systems. A flare can hit at any moment from any one of the 14 stars, and pinpointing the exact culprit requires rapid follow-up observations across multiple wavelengths. Perhaps the most insidious cause of erratic light is the vast amount of dusty debris and gas swirling throughout the system. We're not just talking about neat protoplanetary disks. We're talking about a complicated interstellar environment filled with the tidal tails, ejected material, and debris from past collisions. This dust doesn't just sit there, it moves. Large clouds of this fine material can drift across our line of sight to individual stars, causing long, slow, and asymmetrical dimming events that can last for months or even years. The star doesn't blink out, it gradually fades and then gradually brightens again as the cloud passes. This isn't a clean, repeatable eclipse, it's a singular, unpredictable obscuration event. For an observer, it looks like a star is slowly being dimmed by a giant, invisible hand, a phenomenon that can easily be mistaken for something far more exotic if not carefully analyzed. The result of all this is a light curve that is a unique fingerprint of the system's incredible complexity. It contains encoded information about orbital periods, stellar sizes, flare activity, and the distribution of interstellar dust, all mixed together into one incredibly messy but data-rich signal. Decoding it is one of the greatest challenges in modern observational astronomy. It requires sophisticated computer algorithms that can run millions of simulations, testing different combinations of eclipsing binaries, flare stars, and dust clouds to find a model that reproduces the wild, seemingly random fluctuations actually recorded by the telescope. It's a monumental computational effort, but the reward is a profoundly detailed understanding of the system's structure and physics that would be impossible to gain any other way. This erratic light, a nightmare to sort through, is ultimately our most direct window into the beautiful chaos of 14 stars living their lives intertwined. And this gravitational influence reaches far beyond the boundaries of the system itself, acting as a cosmic catalyst for new creation. The vast collective mass of 14 stars and their powerful movements generate profound shockwaves that travel through the surrounding interstellar medium. As these stars orbit, their combined gravity tugs on nearby clouds of cold gas and dust, while stellar winds and past supernova within the system send actual physical pressure waves rippling outward at supersonic speeds. These waves act like a giant celestial hand, reaching into quiet nebulae and compressing them, squeezing the thin gas into dense, critical pockets. In these newly pressurized regions, the delicate balance is shattered. The inward pull of gravity suddenly overwhelms the gas's internal pressure, and a process that might have taken millions of years naturally is triggered almost instantaneously. A once peaceful cloud begins to fragment and collapse, giving birth to a new generation of stars, all sparked into existence by the chaotic dance of their colossal neighbors. We see the evidence for this process in stunning astronomical images that show a Quattuordecuple system positioned right on the edge of a bright, glowing nebula, with several obvious, much younger protostars embedded within the cloud's material. The geometry is a dead giveaway. The oldest stars are in the complex system at the center, and surrounding them, tracing the edge of the shockwave they created, are pockets of new stellar formation. It's a cosmic chain reaction, a stellar family literally creating its own descendants and neighbors through its sheer gravitational influence. The triggered stars will always be noticeably younger than the system that created them, a clear chronological signature of the cause and effect relationship. This makes a Quattuordecuple system not just an isolated island of stars, but the engine of a small-scale star-forming region, a patriarch whose dynamic life directly seeds the birth of new suns around it. The implications of this are profound for how we understand the evolution of our galaxy. Star formation isn't always a slow, isolated process. It can be a contagious phenomenon, spreading from one energetic event to the next. A single, massive, complex system can set off a wave of creation that propagates through a molecular cloud, dramatically increasing the rate of star birth in its corner of the galaxy. This process enriches the galactic environment, ensuring that the heavy elements forged in the hearts of the largest stars and dispersed in supernova are directly incorporated into the next generation of stars and planets. The triggered stars are born into an environment already pre-seeded with the complex chemistry necessary for planet formation, and potentially the building blocks of life itself, all thanks to the tumultuous activity of their 14 parent progenitor. Yet for all the intricate connections that bind these 14 stars together, some of the most gravitationally bound members are almost impossible to find, existing so far from the brilliant core that they seem like lonely, isolated wanderers. These are the system's ultra-wide companions, stars that trace such vast, lazy orbits around the central chaos that a single circuit could take tens of millions of years to complete. Discovering these distant partners was less about seeing a direct link and more about a painstaking cosmic census, meticulously mapping the motion of every star in a particular region of the sky, and noticing that one faint, seemingly solitary star was moving in perfect lockstep with the complex system light years away. Their shared velocity through the galaxy was the giveaway, a silent testament to a gravitational connection so faint it's almost negligible, yet strong enough to persist over eons. The existence of these companions stretches the very definition of a star system to its breaking point. We are accustomed to systems like our own, where the sun's influence, while immense, has a clear boundary at the Oort cloud. But here, gravity's reach is so extended that a star separated by trillions of miles, a distance that could comfortably contain thousands of solar systems, is still considered a part of the family. The force holding them together is almost unimaginably weak, a whisper of attraction that is constantly challenged by the gentle gravitational tugs from other passing stars and the tidal forces of the galaxy itself. That these bonds can survive in such a tenuous state for billions of years forces us to reconsider the durability of gravitational connections on the very largest scales. Their incredibly long orbital periods present a unique challenge for astronomers. We haven't been observing the heavens for long enough to see even a fraction of 1% of a single orbit for these ultra-wide partners. Their paths must be inferred through complex models and precise measurements of their current position and velocity. Confirming their membership is an exercise in celestial forensics, ruling out every other possibility until the only explanation left is a gravitational bond of incredible patience and scale. These stars are the ultimate testament to the system's gravitational influence, proving that its dominance extends into a realm of space we would otherwise consider empty and solitary. And just when we thought the gravitational interplay was complex, we find evidence of an even more intimate connection, one that links the stars not just by the silent pull of gravity, but by invisible dynamic bridges of pure force. Observations of close binaries within these 14 star families have revealed a phenomenon that sounds like it's straight out of theoretical physics: magnetic field entanglement. In these pairs, the stars are so close and their interactions so violent that their powerful, individual magnetic fields don't just interact. They can become fundamentally linked, weaving together into a single, complex web that connects their atmospheres and dictates their most violent outbursts in perfect, terrifying synchronization. To understand how this works, picture two stars locked in a tight, fast orbit. Each star has its own powerful magnetic field, a vast, invisible structure that extends far out into space, much like the field that surrounds our Earth but immensely stronger. In isolated stars, these fields are mostly self-contained, but when two such stars orbit extremely close to one another, their magnetic environments are forced to overlap. They don't simply bounce off each other. Under the right conditions, their field lines can actually break and reconnect, tethering one star directly to the other with strands of immense magnetic force. It's as if the stars are connected by colossal, twisting elastic bands made of pure energy, constantly stretching, snapping, and reforming as the stars whirl around each other. This entanglement creates a direct highway for energy and matter between the two stars. The most dramatic consequence is coordinated flaring. Imagine one star building up tension in its magnetic field, preparing for a colossal superflare. In an isolated star, that energy would release locally, but in an entangled pair, the pent-up energy can propagate along these connected magnetic field lines, triggering a sympathetic eruption on its companion stars simultaneously. Astronomers have observed these events, two stars separated by millions of miles, erupting in perfect, synchronized tandem with identical light curves, their combined energy output creating a flash that can briefly outshine the rest of the system. It's a stunning demonstration that they are no longer acting as independent entities, but as two components of a single, interconnected electrical circuit. The resulting structure around the binary is known as a shared magnetosphere, a vast and turbulent region where the magnetic fields of both stars are merged into a chaotic, unpredictable soup of forces. Within this region, the behavior of charged particles like those in the stellar winds blasting off their surfaces becomes utterly bizarre. Particles can be accelerated to near light speed, funneled from the atmosphere of one star directly onto the surface of the other, or trapped in endless loops between them, glowing with intense radiation. This creates a constant, high-energy environment that would be instantly lethal to any potential planets and would fundamentally alter the chemistry of any surrounding protoplanetary disks, bombarding them with a relentless rain of energetic particles. Discovering this required a unique combination of tools. X-ray and radio telescopes were key, as these wavelengths of light are directly emitted by the high-energy processes happening within these entangled magnetic fields. By watching a flare erupt in X-rays and then seeing an identical spike in radio waves from the other star milliseconds later, astronomers could trace the path of the energy and confirm the connection. It's a level of interaction that goes far beyond gravity, revealing a universe where stars are not just distant points of light, but active, dynamic bodies that can literally reach out and touch each other with forces that shape their evolution and their fate in the most profound ways. Within this chaotic gravitational arena, the very fabric of matter is constantly being torn apart and reassembled in a relentless cycle. The system acts as both a prolific factory and a ruthless destroyer of cosmic dust, those tiny specks of silicon carbon and silicate that are the fundamental building blocks of planets and ultimately life itself. This dynamic is driven by the stark contrast between the various stars. The massive hot blue stars blast out fierce stellar winds, a hurricane of charged particles that constantly sandblast the surfaces of their cooler, dustier siblings. This process, called sputtering, acts like a cosmic pressure washer, knocking individual atoms loose from dust grains and slowly eroding them away into their constituent gas. Meanwhile, the intense ultraviolet radiation from these same hot stars bombards any surrounding dust clouds, heating them to the point where the delicate ices that glue smaller particles together simply vaporize, causing smaller dust grains to disintegrate entirely. Yet, even as destruction reigns in some corners, creation is flourishing in others. The cooler red giants and asymptotic giant branch stars are the system's primary dust factories. These bloated, aging stars have extended, turbulent atmospheres where temperatures are just right for atoms to condense out of the gas phase and form solid particles. Elements like carbon, oxygen, silicon, and iron created in the star's nuclear furnace are pushed to the surface by convection, and in the cooler outer layers they stick together. The star's powerful stellar wind then carries this newly forged dust away, expelling it into the surrounding space in vast, smoky clouds that expand outward for trillions of miles. Furthermore, the frequent gravitational encounters and potential collisions between smaller bodies in the system generate enormous quantities of fresh dust through grinding and violent impacts, constantly replenishing the supply. This entire cycle of creation and destruction is painted across the sky in the light we cannot see with our eyes but can detect clearly with infrared telescopes. The tiny dust grains absorb the intense visible and ultraviolet light from the hot stars and re-emit that energy as heat in the form of infrared radiation. This makes the entire system blaze brilliantly in the infrared part of the spectrum, appearing as a complex, intricate nebula of glowing dust that intertwines with the points of starlight. By analyzing the specific infrared signatures, astronomers can read the composition of the dust like a chemical barcode, identifying regions rich in carbon-based graphite grains, others filled with silicate minerals akin to sand, and still others showing the telltale signs of more complex ices and organic molecules. This dusty environment is not a static backdrop. It is a vibrant, evolving ecosystem, a constant tug of war between the forces that build the foundations of new worlds and the forces that seek to tear them down. But perhaps the most profound and far-reaching consequence of this intricate gravitational dance is written not in light, but in the fabric of space-time itself. Every single one of these 14 star systems is in effect a colossal factory for the most elusive signal in the universe, gravitational waves. These are the ripples in the fabric of reality predicted by Einstein, generated whenever massive objects accelerate. In a Quattuordecuple system, that acceleration is constant and extreme, especially within the tightest binary pairs. As these stars whip around each other at incredible speeds, they stir the very cosmos, sending out a continuous, faint hum of gravitational radiation that propagates outward at the speed of light. For most of these systems, this hum is too quiet to be detected across the vast interstellar distances, a whisper lost in the cosmic static. However, this emission of energy comes at a direct cost to the stars themselves. The gravitational waves carry away orbital energy, and that lost energy has to come from somewhere. It is slowly but inexorably siphoned from the motion of the stars, causing their orbits to decay. Imagine a satellite in low Earth orbit gradually slowing down and falling closer to the planet. The same principle applies here, but on a cosmic scale and over millions of years. For a wide, stable binary, this process is negligible. But for the ultra-tight inner binaries found in these hierarchical systems, pairs that might orbit each other in a matter of hours, this orbital decay is a relentless countdown clock. With every rotation, they lose a tiny amount of energy, spiraling imperceptibly closer together, destined for a final, catastrophic merger. This makes these Quattuordecuple systems the ultimate precursors, the long-sought missing link that explains the origins of the colossal black hole and neutron star mergers detected by observatories like LIGO and Virgo. We observe the stunning end product, two massive, dark objects colliding in a universe-shaking event, but the question has always been, how do such massive objects get so close together without first disrupting each other? The answer is unfolding right here in these complex families. The intricate hierarchy provides the perfect cradle. The gravitational nudges from the many outer stars can gradually force an inner binary into an ever tighter orbit, a process known as quasi-Lidov oscillations. Once the pair is sufficiently close, the emission of gravitational waves takes over, seamlessly continuing the inward spiral that was begun by its stellar siblings. The final moments of this cosmic countdown are among the most violent events since the Big Bang. If the inspiraling pair consists of two neutron stars, their collision will forge heavy elements like gold and platinum in staggering quantities, scattering them across the galaxy. A merger between two black holes will release more energy in a fraction of a second than all the stars in the observable universe combined, all in the form of pure gravitational waves. The system that created them, now missing two of its members, would undergo a dramatic gravitational reconfiguration, potentially ejecting more stars or settling into a new, stable arrangement with 12 suns, forever marked by the cataclysm that occurred in its heart. These 14 star marvels are not just curiosities, they are the cosmic engines that forge the most extreme events in the universe, setting the stage for collisions that literally shake the foundations of reality. This brings us to a fundamental challenge that has haunted astronomers since the very first hints of these systems emerged, the possibility that it's all a grand illusion. When you point a telescope at a dense star field and see 14 points of light clustered together, your first assumption cannot be that they are a family. The universe is vast and the third dimension is hidden from us. It is entirely possible, even likely, that many of those stars are simply strangers passing in the night, aligned by pure chance along our line of sight, a foreground star, a background star, and another so far away they merely appear to be neighbors from our limited earthly perspective. Ruling out this chance alignment is perhaps the most painstaking and critical piece of detective work in confirming a true quattuordecuple system. The tool for this cosmic verification is a combination of two exquisitely precise measurements: proper motion and radial velocity. Proper motion tracks the tiny, gradual shift of a star's position on the celestial sphere over years, the slow drift of its pinprick of light against the backdrop of infinitely more distant stars. If two stars are truly bound, they must share a common path through space. Their proper motions will be identical, moving in the same direction at the same rate. If even one star in the group is moving on a completely different vector, it's an imposter, a background or foreground object that just happens to be in the way. But this is only half the story, because two unbound stars could, by sheer luck, be moving in the same direction across our sky. This is where radial velocity provides the clinching evidence. Using the Doppler effect on the star's light, astronomers can measure whether it is moving toward us or away from us. A gravitationally bound family doesn't just travel together across the sky, they also travel together through space. This means all members must share the same radial velocity, the same precise speed along our line of sight. If one star is hurtling toward us while its apparent neighbor is racing away, the illusion is shattered. They are not a system. Proving a quattuordecuple system requires obtaining both proper motion and radial velocity data for every single one of the 14 candidates, and showing that their values are statistically identical within minute margins of error. This is not a quick process. It demands years, sometimes decades, of repeated observations with the world's most stable and precise instruments. A single measurement is meaningless. You need a long baseline of data to detect the tiny, consistent motions that prove a shared destiny. It's a testament to human patience and technological advancement that we can even attempt this. The payoff, however, is the profound satisfaction of transforming a celestial coincidence into a confirmed cosmic reality, of knowing with certainty that we are looking at a true gravitational family of 14 suns, a rare and magnificent configuration in our galaxy. These 14 star marvels are far more than just a spectacular cosmic oddity. They are living fossils, time capsules that hold secrets from the galaxy's tumultuous youth. Their very existence provides a direct and powerful link to a bygone era, a window into a time when the Milky Way was a far denser, more chaotic, and more violent place. By studying their motions and their unique chemical compositions, astronomers are practicing a form of galactic archaeology, using these rare systems as ancient texts to decipher the conditions under which our galaxy first took shape. To understand why they are such powerful relics, we have to journey back billions of years. The prevailing theory of galaxy formation suggests that the early Milky Way was not the grand, ordered spiral we see today. It was a sprawling, clumpy conglomerate of gas and dark matter, filled with incredibly dense and massive star clusters. In these crowded stellar nurseries, stars were born cheek by jowl, with distances between them far smaller than we see in our modern galactic neighborhood. This high-density environment was a cosmic demolition derby, where close encounters, gravitational captures, and even direct collisions were not rare events, they were the norm. It was in this frenzied environment that complex multi-star systems had the highest probability of forming and surviving their volatile infancy. This makes a stable quattuordecuple system not just a random occurrence, but a likely survivor from that ancient epoch. Its intricate hierarchical structure is a fossilized record of those early, frequent gravitational interactions. The wild misalignments of its orbital planes are like a preserved crime scene, showing us that this system wasn't born from one quiet cloud, but was assembled through a series of dramatic captures and mergers that could only happen in a densely packed cluster. When we observe its 14 stars today, we are essentially looking at a snapshot of the galactic environment as it existed over 10 billion years ago. A relic that has persisted long after its birthplace cluster has likely dissipated into the general galactic disk. The evidence for this ancient origin is written not just in their orbits but in their very atoms. Spectroscopic studies have revealed that many of these systems are incredibly metal-poor. In astronomy, metals refer to any element heavier than hydrogen and helium. Since these heavier elements are forged in the hearts of stars and scattered by their deaths, the abundance of metals in a star is a direct clock. The first stars in the universe were made of pure hydrogen and helium. They lived fast, died young in supernova, and seeded the cosmos with the first heavy elements. Stars that formed from this newly enriched gas contain a small fraction of these metals. Each subsequent generation of stars becomes more and more metal-rich. The strikingly low metal content found in many of these complex systems is a clear signature that they are members of the galaxy's first or second stellar generation. They formed from gas that had been polluted by only a handful of the very first supernova. This means they are among the oldest structures in the entire Milky Way, ancient enough to have witnessed the galaxy's formative years. Their survival for such an immense span of time is a testament to the remarkable stability of their hierarchical orbits, a delicate balance that has allowed them to endure through eons of galactic evolution while countless other systems were torn apart. By tracing their paths through the galaxy, a field known as galactic dynamics, we gain even more insight. These systems don't just orbit the galactic center in neat, circular paths like younger, metal-rich stars in the disk. Instead, they often follow highly eccentric, tilted, and wobbly orbits that take them far above and below the galactic plane on long, looping journeys. These peculiar trajectories are characteristic of the galaxy's stellar halo, a vast spherical cloud of old stars that represents the primordial foundation of the Milky Way. Their motion is a ghostly echo of the chaotic mergers and accretion events that built our galaxy, a dynamic fingerprint proving they have been there since the beginning, untouched by the later settling of gas and dust that formed the orderly spiral disk. This makes each Quattuordecuple system a singularly valuable data point. They are not just ancient, they are complex ancient structures. A single old halo star gives us 1 point of chemical and kinematic data. But a bound system of 14 such stars gives us 14 interconnected points, plus the precise gravitational history that has locked them together for billions of years. It allows us to test our models of galactic evolution with an unparalleled level of detail. By running sophisticated simulations that attempt to form and preserve such a system from the early universe to the present day, we can reverse engineer the conditions of the primordial Milky Way. If our simulations can only create a system like this under specific early conditions, a certain cluster density, a particular rate of interactions, then finding one in reality powerfully confirms that those conditions must have existed. In this way, these rare stellar families are doing more than just telling us about their own history. They are helping us write the first chapters of our galaxy's biography. They provide direct, observational constraints on one of the most elusive periods of cosmic history, a time when the first structures were assembling themselves out of the pristine gas of the early universe. Every measurement of their motion, every analysis of their chemical makeup, adds another piece to the puzzle, helping us understand the frantic, crowded, and violent nursery that gave birth to the Milky Way and allowed for the existence of such breathtakingly complex gravitational wonders. Attempting to recreate even a fraction of this cosmic complexity inside a computer is a task that pushes the very limits of modern technology and our understanding of physics. The primary tool for this Herculean effort is something known as an n-body simulation. The n stands for the number of individual objects, in this case 14 stars, each with its own mass, velocity, and gravitational pull that the software must track. The challenge is that every single star exerts a gravitational force on every other star all the time. This doesn't sound so bad with just a few objects, but the computational cost doesn't just increase with each new star, it explodes. The number of calculations required scales with n squared. For a mere 14 stars, that's already 196 individual gravitational interactions that must be computed for every single infinitesimally small time step of the simulation. And to model even a few thousand years of cosmic evolution, you need to calculate these trillions upon trillions of interactions. These aren't simulations you can run on a home computer. They demand the raw power of the world's most advanced supercomputers, machines with hundreds of thousands of processor cores working in parallel for weeks or even months at a time. The codes themselves are marvels of modern astrophysics, employing fiendishly clever algorithms to try and make the problem slightly more manageable. They use techniques like Barnes hut trees, which group distant stars together as a single gravitational point to reduce the number of calculations, or symplectic integrators, which are designed to conserve energy and maintain stability over these incredibly long runtimes. Despite these computational shortcuts, the simulations remain brutally expensive, chewing through immense processing power just to model a tiny sliver of cosmic time. Yet for all this staggering effort, the results are often humbling. When astrophysicists set up a virtual Quattuordecuple system based on the best observational data, inputting the measured masses and estimated starting velocities, and then set the simulation in motion, the outcome is frequently chaos. Instead of settling into the beautiful, stable hierarchical dance we actually observe in the real universe, the virtual system often becomes a gravitational catastrophe. Stars are sent careening into each other, others are flung out into the void, and the entire delicate structure unravels in a matter of a few million simulated years, a blink of an eye on the cosmic scale. This isn't just a minor discrepancy, it's a fundamental failure of our models to replicate the serene longevity we see through our telescopes. This persistent gap between simulation and reality is one of the most exciting and frustrating puzzles in theoretical astrophysics today. It strongly suggests that our models are missing a key piece of physics, some crucial ingredient that acts as a stabilizing force or a damping mechanism within these incredibly complex environments. The leading hypothesis is that we are not fully accounting for the subtle, smoothing influence of the surrounding material, the vast reservoirs of gas and dust that permeate these young systems. This diffuse material, while not massive compared to the stars, could provide a form of gravitational friction, absorbing energy from the most chaotic interactions and helping to circularize and stabilize orbits over time. Alternatively, the magnetic field interactions between stars and their disks, or even subtle relativistic effects in the tightest binaries, could be providing the missing stabilizing influence that our current, simpler Newtonian gravity models don't include. Every time a simulation fails to match the observed stability of a real Quattuordecuple system, it isn't a defeat, it's a clue. It forces physicists back to the drawing board to invent new algorithms, incorporate new physics, and question old assumptions. These digital laboratories, for all their limitations, are essential proving grounds. They allow us to test which theories of formation and stability hold up under pressure and which ones crumble into digital dust. The very fact that the universe can effortlessly maintain an order that our most powerful machines cannot replicate is a powerful reminder that nature still holds deep secrets, waiting for us to develop the tools and the insight to finally understand them. But for all their grandeur and mystery, observing the intricate details of a Quattuordecuple star system has always been like trying to discern the features of a face from a mile away through a dense fog. Our current telescopes, for all their power, have simply reached their limit. The incredible distance, the mind-bogglingly close angles between stellar components, and the faint, delicate light of the most interesting features like protoplanetary disks and ejected tidal tails have remained frustratingly just out of reach. This is why these 14 star marvels represent the ultimate first light challenge. the celestial puzzle that the next generation of astronomical giants, like the James Webb Space Telescope and the upcoming Extremely Large Telescope, were practically designed to solve. The James Webb Space Telescope, or JWST, brings two revolutionary capabilities to this problem. Its unprecedented sensitivity to infrared light is an absolute game changer. Remember all that complex, warm dust and those protoplanetary disks we discussed? They glow brightest not in the visible light our eyes see, but in the infrared part of the spectrum. Where the Hubble Space Telescope saw maybe a faint smudge of haze around a star, JWST sees intricate structure, revealing the detailed rings, gaps, and spiral arms within those planet-forming nurseries. It can peer directly through the vast clouds of dust that often shroud these systems, seeing the stellar newborns within. Furthermore, its location at the L2 Lagrange point, far from the warmth and interference of Earth, combined with its massive, gold-plated beryllium mirrors, gives it a clarity and a light-gathering power that allows it to not just see that there are 14 points of light, but to analyze the unique atmospheric composition of each individual star within the system, even the faint, cool one. Previously lost in the glare of their brilliant siblings, yet even JWST has its limitations, primarily its resolution, its ability to distinguish two incredibly close objects as separate. This is where the ground-based behemoths come in. The extremely large telescope, currently being built on a mountaintop in Chile, is a project of almost unimaginable scale. Its main mirror will be an astounding 39 meters across, nearly as wide as a basketball court. This colossal light bucket, combined with a technology called adaptive optics, which uses laser guide stars to measure and cancel out the blurring effects of Earth's atmosphere in real time, will provide a level of sharpness that dwarfs anything we have today. The ELT will be able to do something that has until now been purely theoretical. It will directly image and track the individual orbits of stars within the tightest binary pairs in these systems. We will no longer have to infer their dance from subtle wobbles in their light. We will watch them move in real time over just a few years, tracing their precise elliptical paths with stunning accuracy. The synergy between these observatories will be where the true magic happens. JWST, from its pristine vantage point in space, will provide exquisitely detailed chemical and thermal data on each component. It will tell us what each star is made of, how dusty its environment is, and the temperature of its protoplanetary disk. The ELT from the ground will provide the breathtakingly precise astrometric data of the exact positions and motions of each of those components over time. By combining these two datasets, astronomers will be able to create the first truly complete and dynamic model of a Quattuordecuple system. We will be able to calculate the exact masses of the stars, understand the true structure of their gravitational bonds, and even detect the subtle tug of those hidden objects, the suspected black holes and brown dwarfs, by seeing their gravitational influence on the orbits of the stars we can see. This isn't just about getting a prettier picture, it's about finally being able to run the ultimate cosmic test. For decades, we have had sophisticated computer models that try to explain how these systems form and remain stable. But those models have been built on a foundation of incomplete and low-resolution data. We've been trying to reverse engineer a masterpiece while only being able to see a few of its brushstrokes. The data flood from JWST and the ELT will provide the complete high-definition image. We can feed these precise masses, orbits, and compositions into our simulations and see, once and for all, which theories hold up. Do the resonant orbits we've postulated actually exist? Does the hierarchical structure perfectly match what our models predict? This will either beautifully confirm our understanding of celestial mechanics or, far more excitingly, reveal glaring flaws that force a revolutionary new way of thinking about gravity and orbital dynamics on the most extreme scales. Yet for all their celestial beauty, these 14 star systems are far more than just cosmic wonders. They are the universe's most extreme natural laboratories, offering physicists a testing ground for fundamental laws under conditions we could never hope to recreate on Earth. Within their complex gravitational fields, we can observe the delicate dance of general relativity playing out in real time. The incredibly tight orbits of the innermost binary pairs provide a perfect environment to witness phenomena like the precession of periastron, a gradual wobble in the orientation of a star's elliptical orbit caused by the curvature of spacetime around its massive companion. This subtle effect, a key prediction of Einstein's theory, is incredibly difficult to measure in most systems. But here, with stars whipping around each other at fantastic speeds, the precession is amplified, allowing us to test the limits of general relativity with a precision that was once thought impossible. The study of orbital dynamics, the very rules that govern how objects move under the influence of gravity, is also pushed to its absolute limits within this chaotic environment. Our solar system, with its single dominant mass and relatively well-behaved planets, is a simple classroom example. A Quattuordecuple system is the advanced postgraduate course where all the simplifications break down. Here, we must account for the gravitational influence of not one or two, but 13 other massive bodies, each pulling and tweaking every orbit in a constantly shifting calculation. This forces us to move beyond the tidy two-body problem and into the realm of chaotic n-body interactions, developing new mathematical models and computational techniques to even begin to predict their long-term stability. Each stable configuration we find is a victory for our understanding of physics, while every unstable simulation that flies apart tells us there is still something fundamental we have yet to learn. Beyond gravity, these systems are also unparalleled natural accelerators for high-energy particle physics. The intense magnetic fields entangled between close binaries, combined with the powerful shock fronts where stellar winds collide at thousands of kilometers per second, create environments where particles are accelerated to energies far beyond the reach of the Large Hadron Collider. These natural accelerators produce a constant rain of high-energy radiation, from X-rays to gamma rays, allowing us to study how matter behaves under the most extreme conditions imaginable. We can observe how protons and electrons are whipped to near light speed, how magnetic reconnection events release staggering amounts of energy, and how turbulent plasmas behave in the presence of unimaginably strong gravitational and magnetic forces, all from a safe distance courtesy of the cosmos. The field of stellar evolution finds its most dramatic test cases here as well. In a typical setting, a star's life path is largely determined by its initial mass. But in this crowded environment, that simple story is constantly being rewritten. We can observe stellar rejuvenation through mass transfer and mergers in action, watching as stars are torn apart, rebuilt, and have their evolutionary clocks reset right before our eyes. The presence of white dwarfs and neutron stars that have survived supernova without being ejected forces us to refine our models of these catastrophic explosions, telling us they can be far more symmetric and orderly than we once believed. This laboratory provides the entire life cycle of stars, from their turbulent birth in triggered nebulae to their often violent deaths, all contained within a single, interconnected family, offering a complete picture of stellar ecology that we can study from beginning to end. After decades of searching the vast expanse of our galaxy with ever more powerful instruments, the final and perhaps most humbling discovery about these celestial families is their profound and staggering rarity. For all their grandeur and complexity, confirmed Quattuordecuple star systems are among the rarest gravitationally bound structures we have ever identified. Current estimates suggest there may be only a handful of them scattered among the several 100 billion stars that make up the Milky Way. To put that into perspective, finding one is like searching for a single, specific house across a continent the size of North America, blindfolded. This extreme scarcity is the ultimate testament to the knife's edge of conditions required for their formation and long-term survival, a precise recipe of dense birth environments, gentle gravitational captures, and the immediate finding of a stable resonant lock that has likely failed countless times elsewhere. This rarity does not discourage astronomers, it fuels an insatiable hunt. The search for more of these systems is a primary science driver for some of the most ambitious astronomical surveys ever conceived. Projects like the European Space Agency's Gaia mission are revolutionizing this quest. Gaia is not a traditional telescope that takes pretty pictures. It is a supreme celestial cartographer, meticulously measuring the position, distance, and motion of over 1 billion stars with unprecedented precision. Its immense value lies in its ability to perform a galactic-scale census, identifying stars that share a common proper motion, that telltale drift across the sky that betrays a gravitational bond. By sifting through Gaia's colossal dataset with sophisticated algorithms, astronomers can flag small clusters of stars moving in perfect lockstep, which are then followed up with ground-based telescopes to measure their radial velocities and confirm they are true family members, not just strangers in the night. The Vera C. Rubin Observatory, poised to begin its legacy survey of space and time, will add a powerful new dimension to this search: time. This facility will photograph the entire visible sky every few nights for a decade, creating an unimaginably detailed movie of the cosmos. This relentless monitoring is perfectly suited to detecting the complex, erratic light curves that are the signature of these systems. It will catch the eclipses of multiple binaries, the violent flare-ups from magnetic entanglement, and the slow dimming from passing dust clouds, automatically flagging the most variable and bizarre objects in the sky for further study. The hope is that between Gaia's precise mapping and Rubin's relentless monitoring, we will move from knowing of a few rare examples to having a true statistical sample of these extreme systems. Discovering more of them is about much more than just adding to a list of cosmic curiosities. The ultimate goal is to answer a foundational question in astronomy: what is the upper limit to stellar multiplicity? How many stars can nature possibly bind together with gravity before the entire structure becomes inherently unstable and instantly flies apart? Is 14 the practical maximum, or is it merely the most complex configuration we have been able to confirm with our current technology? Could there be a system of 16 or even 20 stars lurking in the dense galactic core, hidden from our view by dust and distance? The confirmed existence of even one system with a higher number of stars would immediately rewrite our models of celestial mechanics, forcing us to accept that the universe is capable of an even more profound level of complexity and order than we currently believe. The population statistics of these systems, once we have a larger sample, will act as a direct probe into the conditions of the earliest universe. If they are indeed relics from a time of denser star clusters, as their metal-poor compositions suggest, then the number we find and their distribution in the galaxy's halo should match the predictions of our models of galactic formation. Finding more of them than predicted would tell us that the primordial Milky Way was even more crowded and chaotic than we think. Finding fewer would suggest that our current theories overestimate the efficiency of these gravitational capture processes. Each new Quattuordecuple system discovered is not just another object in the catalog. It is a data point in a grand cosmic experiment, a critical piece of evidence that helps us understand the physical laws and initial conditions that shaped our galaxy's infancy and set the stage for everything that followed, including our own solitary solar system. Their extreme rarity makes each one a precious and invaluable key to unlocking the universe's deepest secrets. From the impossible stability of 14 suns locked in a delicate gravitational harmony to the baffling presence of planets forming in what should be a chaotic demolition derby of gravity, these systems defy our every expectation. We've journeyed through a realm where stars are catapulted into the intergalactic void as hypervelocity fugitives, where the dead remains of supernova linger as gravitational anchors, and where the very fabric of space-time is rippled by the relentless dance of these colossal masses. We've witnessed stellar zombies, cosmic chemistry labs in swirling tidal tails, and the breathtaking precision of resonant orbits that function like a grand celestial symphony. Each discovery peels back a layer, revealing a universe far more inventive, violent, and beautifully ordered than we ever dreamed. These quattuordecuple systems are more than just astronomical curiosities. They are the ultimate frontier of stellar dynamics. They are natural laboratories where the laws of physics are stress-tested to their absolute limits, forcing us to question, revise, and expand our understanding of gravity, formation, and evolution. They represent the extreme edge of what is possible, a masterclass in chaos and order written in starlight. They challenge us to build bigger telescopes, to write more sophisticated simulations, and to keep looking up with a sense of wonder and humility. Now we want to hear from you. With 30 strange discoveries to choose from, which one completely rewired your brain? Was it the idea of a sky with 13 other suns? The cosmic slingshot ejecting stars forever? Or the gentle, musical resonance that keeps this entire chaotic family from tearing itself apart? Let us know in the comments below which discovery amazed you the most. If this journey to the edge of known physics captivated you, make sure to subscribe and hit the bell so you don't miss our next deep dive into the universe's greatest mysteries. The cosmos is vast, strange, and waiting for us to explore it together.